Welcome back. So today we're going to dive into defining and using data structures in assembly language for both legacy assemblers like EDTASM Plus and modern assemblers like LWASM and KASM. So grab a banana and stick around. Alrighty. So I figured I would step away a little from covering projects like Alter Ego and Space Pirate Kumiko and share some of the information and techniques that really help drive their development. Now, since both of those projects are powered by chaos, which is heavily driven by data structures, I thought that it might be a really good place to start. So what are data structures, you ask? Well, simply put, a data structure is a specialized way of organizing, managing, and accessing data. It's really just a collection of data values, which can be primitives such as integers, addresses, or pointers, if you will, or even other data structures. In fact, composition is very common across a wide number of paradigms. Now, for our discussion, I should note that the elements of a data structure are usually referred to as members or fields. Now, I'm going to be referring to them as members here, mostly because I don't think I've referred to them as fields in probably 30 or 35 years. Now, if you're familiar with high-level languages like C, then you know that declaring and using data structures in those languages are incredibly simple. But in assembly language, though, you might find it a little daunting because while it's fairly easy to define them, at the start of the project, managing them through the development of a project can be quite difficult, depending on both how you define them, as well as what assembler you happen to be using. So today I'm going to take you through several different ways to define data structures in your assembly code and use some and some of the difficulties that you might encounter along the way. I'm going to be covering this in examples for three different categories of compilers, or I'm sorry, assemblers, not compilers, assemblers. So the first category is going to be those that do not support data structures as a feature of the assembler. And a lot of the legacy assemblers like EDTASM Plus, EDTASM 3 from Circomp, they don't support data structures at all. Now there are some that do. I believe Macro ADC was one that did support data structures, but by and large there was a pretty large gap in support to that. Now the second category is going to be kind of more modern assemblers, along with some of those legacy assemblers like Macro ADC that do support data structures as a feature of the assembler. Assemblers like LWASM and KASM have pretty good support for that. Now the last category is actually one that I don't think there's a whole lot of assemblers that fall into it, because this category is going to be those that support data structures and inheritance, which for chaos is just crucial for not just for its implementation, for even using it. You have to embrace not just data structures but inheritance in order to use that. So let's get started and define a data structure for our examples. Now, since I'm a game developer, and you probably want to be one too, I decided to go with something pretty simple that represents a sprite on the display. Nothing too fancy. Now, for our sprite, we're going to create a simple data structure that includes only three members. A single byte identifier so that we know which image to draw, along with the X and Y position of where we want it to be drawn on the display. Now, the first approach that I'm going to show on how to define and use the sprite in assembly language should work with all assemblers that support the equate or EQU instruction. But before we even get into that, we should probably also take a step back and decide how we're going to name our members and take into consideration limitations on the length of label names. Now, keep in mind, we only have to do this if we're targeting legacy assemblers. And since we do want to support, EDTASM Plus here, we're going to limit our labels to 6 characters. And if you're using an assembler that supports longer label names, I strongly suggest avoiding the abbreviations like the ones that I'm using in this example. Use full names. Use something that's descriptive, something that you can understand and you don't have to guess. So to get started and define our structure in assembly language, we have to define a a label or a symbol for each member and assign it the offset to where its value exists within the data structure. We start with the image identifier, which is the first one, and it's by far the easiest because it's got an offset of 0. It starts at the very beginning of the data structure. Now, in this example, I'm using an underscore to separate the name of the data structure, which is SPR for sprite in this case, from the name of the member, which here is ID, which fits nicely into 6 characters. This just helps you give an idea of what data you're accessing and what it belongs to, or at least a little bit better of an idea. You don't have to use the underscore. I just prefer to use it whenever possible. Now, unfortunately, this can become quite difficult to do when you're using a symbol like EDTASM Plus, or one that has very limited label sizes. So what I suggest is that regardless of how you decide to name your labels, what naming convention you decide on, definitely take some time before you even get started writing the code to think about what you really want to have in there, so that you already have kind of a plan on how to do that. Even if you don't add them until 6 or 7 weeks down the line, or you don't even think about it until 6 or 7 weeks down the line, you actually have something to go on. So now the next member, the X position, is right after the image identifier, which is only a byte. So it starts at offset 1. Byte's only one character, or 1 byte long, so that's how it is. Now the next member is the Y position, but remember the positions are 16-bit values and take up 2 bytes each. So the offset of the Y position is actually 3. 1 plus 2 equals 3. Pretty simple. Now there's one more member that is helpful to include, but wasn't shown in our example, and is one that specifies the size of the data structure. Now, this is useful when allocating an instance of the data structure, as well as if you have to do something like iterate over an array, so you actually know the size of or the number of bytes that you have to skip in order to get to the next element of that array. Now, of course, in this case, it's 5 characters, because that last member, that Y position, is 2 more bytes, and it starts at 3. Now, accessing the data associated with a sprite becomes a bit easier, regardless of whether you're accessing it directly, say a global, or if you're accessing it indirectly via an index register. So before we can do that, though, we're going to we need to define an instance of our sprite data that we actually can kind of work with here. Now, in our first example, we're going to define it as a global, and that's a little more involved when you in accessing the members. Now, you see since the assembler that we're working with, we assume doesn't have support for data structure, so we're going to define enemy1 and specifically reserve a number of bytes, and we're going to use that sprite size member that we defined earlier. See, it's already helping us, and so now if we needed to allocate multiple instances of the sprite, we can do that too. If we wanted to do it, say as an array, we just multiply the size of the structure by the number of instances that we want. So we want to do 4, then we just do times 4, and that's pretty easy. But for our example, we only need the 1, so that's what we're going to go ahead and stick with. Now, if we want to access the value in the data structure, we just need to do a little bit of math with the symbolics, because we have to take the address of of what we want to access and tell it which member or which offset we want to get from. So now in this case, we've got this will tell the assembler to take the address of enemy1 and add the member of offset assigned to the members label. Now you could of course create labels specific to the contents of enemy1 if you wanted to have say some shorthand, and that may be useful or an option for you. But if you are using a legacy or a native assembler like EDTASM, keep in mind that adding unnecessary labels may cause you to run into problems and run out of space for the symbol table. May not happen, your project may not be that big, but it's certainly something to keep in mind before you even get started. If you're planning something medium or large size, it's definitely something to consider. Now, thankfully, though, accessing it via an index register, which tends to be the more common usage in a lot of cases, particularly for games, is much easier and much cleaner. In this case, you only need to use the member name. You don't have to specify the address there, because that's since the index register already holds the address of the instance, the data structure of that data structure, the member values. can be accessed using only the member label itself. Now, of course, if you need to iterate over an array, as I mentioned earlier, you can advance to the next element using the size that we defined earlier with a simple, load effective address. So if that do draw function or was had to iterate over all of the sprites, you could certainly do that. However you wanted to terminate that loop, whether through a counter comparing to the end of the array. Those options are yours. Now this of course is all great. But one of the problems that you have to keep in mind with this approach is that you need to manage the offsets manually. And while that may not seem like a big deal, it can certainly grow into a huge problem really quickly if you actually don't pay attention to what you're doing. Because anytime that something changes in position or size, all subsequent members have to be updated. So, for example, if we want to move the image identifier from the beginning to the end of the data structure, we have to update every single member except the structure size. That's not a whole lot here, but the larger your data structure becomes, the more tedious and error-prone updating it can be. And if you do this to several of them at the same time, you can certainly introduce problems. Now, although you can't completely eliminate the scenario, you can significantly reduce the potential for problems, especially getting the offsets wrong, which is a problem that you may not even notice for 2 or 3 days or 2 or 3 times, but you may a few hours later or a few days later, and you'll be scratching your head as to why it happened, because that one particular data member that you're now accessing incorrectly is throwing everything off. So to help reduce this, problems like that, we can change the way that we assign the offset when defining the members of the structure. So instead of specifying an explicit offset, we rather than doing that, we reference the preceding member and rely on its size. So it certainly helps to document some of this stuff in comments where you're doing like 2 bytes, 2 bytes, 1 byte, just to kind of keep yourself on track. Now, if we do that, if we insert a member in the middle or even at the beginning of the structure, we only have to update a couple of members instead of everything that follows. Now, of course, on a smaller structure like this one, it's going to look like the changes seem a bit more than you would on a larger structure. But when you do get into those larger structures, you have a much greater distance between the beginning and the end. So when you start placing something, if you place it at the beginning and you have to modify 9 of them versus 2 of them, you're going to pick the option that allows you to only modify 2 of them. But that's all great, and you can certainly get by it. It doesn't eliminate the problems completely. I'll certainly want to make that clear, but it does reduce them significantly. You still have to pay attention. You have to double check it, but usually things are going to go off without a hitch, for the most part. But so what about now? What about assemblers that include support for data structures as part of a feature? Well, I think they're great because not only do they make things much easier, they also usually support macros, which can certainly be utilized to gain pseudo inheritance if your assembler doesn't actually support inheritance as a feature. Now, what is inheritance, you asked? That's a good question too. Simply put, it's a technique that allows a new data structure to inherit all of the members of an existing data structure. Essentially, what you create an extension of that existing data structure. Before we get into that, let's take another step back and start by defining a data structure with an assembler that supports it. Now this is of course much easier, and instead of specifying the offset for each member, we tell the assembler how much space to allocate for it. That's all we have to tell it. We also don't have to come up with any special naming convention like the one using an underscore, and certainly we don't have to use short names because most modern assemblers are going to not going to have those limitations. And the assembler manages all of this for us. It manages all of this for us. We don't have to do anything extra to get to get it. Now, of course, the struct and instruct may be different for the assembler that you're using, so be sure to check the manual. So let's do an example, and just like the last time, we're going to start by defining a single instance of our sprite data. Now the difference here is that instead of specifying an RMB instruction and the size of the structure that we're allocating, we simply use the name of the structure itself as the instruction, and the assembler takes care of everything for us. So the assembler is going to look up and say, oh, okay, sprite is 5 bytes. We're going to reserve 5 bytes for for this or at this address. So it becomes much easier. Now, if you want to access the values in that data structure, um, we use what's commonly referred to as the dot operator. This is used across many different languages, and it's common uses to indicate accessing the member of a data structure or class, or an instance of a data structure or class. Um, so now here we tell the assembler that we want to access a member of an item named enemy1. And what it will do is it'll go out and look up and say, okay, enemy1, what's the offset of y? And it'll go ahead and use that. So your naming is always going to be pretty straightforward. It's always going to be the name of that data structure or the name of that instance dot whatever those members are. So you get some consistency there, and you also get some separation between how you access that instance versus how a global instance versus something that is not. And which we certainly want to take a look at, because accessing it via an index register is very similar, but instead of specifying the name of the instance, we specify the name of the data structure. So we'll still use the dot operator just like we did in the previous example, though. So in this case, it's sprite.y or .x or .id. Now I personally find this to be much cleaner, but that's just my opinion. Now you may have noticed that there's one member that's missing here, and that's the size of the structure. Now when we declared the enemy1 instance as a global, the assembler took care of everything for us as far as determining the size and allocating for it. But what if we needed to iterate over an array of sprites? Say we were using the array in that example, and doDraw did the iteration thingy. So that's where the size of operator comes in, and again, this is similar to the size of operator found in high-level languages like C, where it's used to retrieve the size of a type, just like a data structure. And in this case, we just do a load effective y and then a size of, and the name of either the global instance or the name of the type in parentheses, and that will return the size to us, and then of course comma y to go on to the next one. So having an assembler that supports data structures, definitely helps and eliminates the tedious and error-prone nature of using equates, like you would in something like EDTASM, to define the members as having to manually manage their values, and having to do that in any way. Anytime that you have to do something that can introduce a problem, you want to make sure that you want to do everything you can to avoid it. So if you do have the option of using an assembler that supports data structures as a feature, I definitely recommend using that. But what if I wanted to use the sprite structure as the basis for or the foundation for more complex types? As I was talking earlier in inheritance, what if I wanted to create an enemy structure that had its own data members, but could also be used with all the functions in our example, with the doDraw function in our example? Well, there's actually a couple of ways to do that, and one approach is to use composition. And place an instance of the sprite as the first member of your new data structure. Now what this will do is it will reserve enough space at the beginning of the sprite data members, or for the sprite data members, allowing an instance of enemy to be treated as an instance of sprite. Now what this means is that any instance of enemy can be used with every single function that works with an instance of sprite. So the doDraw function and everything so on would be, you'd be able to pass an instance of enemy to it and not have any problem at all. Now in this example, I've named the member base, but you can name it anything you like. I do recommend, if you do take an approach to composition, make sure it's a short name. Even if it's just an underscore, make sure it's a short name. But in doing this does come with a bit of a downside. So in order to access members of sprite, you have to do it through either the base member of enemy, or alternatively through the sprite data structure name. Now the first way can be tedious if you extend enemy 2 or 3 levels deep, or the latter can make it more difficult to read and understand the code. I mean, that's And that's something that you really want to try to avoid. Now, if we extend, say we extend enemy to big enemy, we start to get a bit ridiculous with having to use the dot operator in order to access the uh, members of that base type or that other type that we're using, that sprite type that we're using. So we have to access it with bigenemy.base.base.id instead of say just bigenemy.id, which not exactly great, but it can certainly get you there. And while composition, does allow us to accomplish what we need to, some people like myself find the use of that base member a bit undesirable. In fact, I would do everything I possibly could to avoid it. Now, that doesn't mean that composition is a bad thing. In fact, composition is an incredibly great thing. It's just sometimes not suitable for working on retro machines in a single language, and it's certainly not the most effective approach for what we're trying to do here. I mean, there's certainly other ways to do it. Best best option is if your assembler actually supports it as a feature, but if it doesn't, then there are other ways in which you can use macros to kind of facilitate a cleaner approach with just a little bit more work on the definition side. Now, it's not really much different than what I've already shown, but it does change where we define the members of a structure. So instead of defining them directly in the structure itself, we instead define them inside of a macro, which we then expand inside of the structure. And this gives us kind of something that we can reuse elsewhere, so that we're not, say copying X, Y, and ID, every time into something else, or updating or modifying it, or doing the composition approach where we have to access, multiple levels of that base member, base.base.base in order just to access a member. God forbid we start using 3 or 4 different data structure names within a small piece of code, which gets even more confusing. So this here changes the definition of a structure into a two-step process, but it simplifies its use and provides symmetry in your code. So now that we've done this, we can extend it and create enemy in just the exact same way. But when we create the macro for it, we include sprite as base as the first member of that, so it expands in the correct order that we need it to in order to access everything. So, and as you go down that line, you start to get the benefits of that deep inheritance, where one particular function works with several different data structures. And when you're working on a game, something like that can be incredibly important. It's because now when we access the members, we only need to worry about accessing a single structure name. And in this case, enemy or big enemy, or even just sprite, if we're at that base level. So it's just a little more work when you define your data structures, but a much cleaner and easier usage, and that's really all there is to it. Using those macros to facilitate filling in the contents of that structured definition comes in incredibly handy in not just this situation, but in others as well. So, once you get used to doing something like that, you'll find other uses for it. Now, I should note that the macro technique is what I started with when I started working on chaos, and it's also which led me to actually adding full support for inheritance to KASM, which is my own assembler. Now, I'm not sure if there are any other assemblers out there for the Cocoa that support inheritance as a feature of the assembler versus a workaround, like with the macros. But I'm going to try and cover it anyway, because if only to plug my own work, I'll be happy with that. Just I got to plug my own stuff in here at some point. So being able to define data structures while also being able to inherit from existing ones makes things much easier, and eliminates the problems and downfalls that I've covered here today, and it removes all that extra stuff that you have to do. It just makes your code less of a pain to deal with. I don't want to say it makes it a joy to deal with, because you're dealing with assembly language here, and if you're working on a project like Digger 3, I mean that was what, 11,500 lines of assembly language code, and that was before the macros were expanded. I mean, that's a lot of code. And when you're dealing with that, it's not going to be fun, but you want to make it as less terrible as you possibly can. And honestly, having a feature like that in your assemblers, that's just cool. That's just really cool. It makes your life so much easier. So let's start with defining or really not even defining it. We just take the sprite structure from our previous example. There's nothing changes since it's acting as the base or really the foundation for all of our other data structures. Now in KASM, when I want to inherit the members of another structure, I don't have to use the macros. I just simply include the name of that existing data structure in the operand field when I declare the structure. So in this case, enemy, I specify sprite as the base type in the operand structure, and that's it. That's all I do. That's it. It's done. Everything is handled by the assembler. All the size, all the offsets. I don't have to use any macros. I don't have to worry about anything. If I change something, it's reflected in everything else that uses it. And we access the members in the same way as we did with the macro technique, and using a single type, and in this case, enemy, which is enemy.lightID or an enemy.id. ID was a member of Sprite, which you had to access through the base member before, and now you don't. So, and the cool thing is that using the inheritance and actually adding it in the assembler just opened up a whole number of enhancements and even more possibilities. Some of which are in development, which and they make working with data structures much easier, especially with when inheritance is introduced into the mix. But those are really outside the scope of this video though. But I'll try to cover those in a future one once they've matured a little bit. But I think that's going to be it for today. I think I'm going to kind of close it up here and um, just kind of sail off, and maybe go to bed or something because it's starting to get late. So it's Sunday night. Have a great week, and I'll see you next time. Bye.